So this is, we have reached 1974.
Sorry.
Yeah, yeah.
Why in manufacturing, why do they still use lightly doped as a to try to get second?
Intrinsic, it's difficult to get intrinsic. So whenever you extract, right, and that's why actually one side thing that I should mention is that one reason why p-type wafers are still used is because it's easier to get these lightly doped p-type wafers, because when you grow them using Tchaikovsky growth, when you dope it with boron, it forms, when you take that crystal out, it comes out to be very nicely uniformly p-doped. If you're going very low in doping, right, you'll see this fluctuation across wafers. So you'll see this fluctuation when you're pulling out that crystal, that your top part would have a certain doping, your bottom part of that crystal will have another doping. So you'll see this cell to cell variation. So it's very difficult to get actually intrinsic kind of wafers. You'll take the crystal out, and maybe you'll pull out an ingot which has has thousands of wafers. You'll get the top 100 to be intrinsic, but then you'll get a gradient across it. So that's why they are pulled off with some amount of wafer. That's a good question. So we have reached 1974. People are routinely using this backside field, and you're using this P plus diffusion from the back by courtesy of this aluminum contact at the back, and so this back contact is formed by aluminum alloying, and which is also happens to be a good p-type dopant for silicon. And you see these textures on the top, and these are to enhance light trapping. That's something we'll talk about in the next lecture. But the efficiencies around this time were around 16 to 17%. Okay, so now the next big thing that happened for these cells was passivation of the surfaces, that is passivation of the emitter and also the passivation of the rear contact. So let me explain, and this was around the 1980s, and even a lot of research at Stanford at that time, headed by Richard Swanson's group, and they were also focusing on this same emitter passivation issue. So let me explain it using this diagram. So I have this electrons and holes that I'm generating over here. I want to collect my electrons using this contact. I want to collect my holes over here, right? But there might be these naughty electrons, or these explorer electrons. Instead of going to the contact, they go over here, right? Or even this guy, maybe instead of going to the contact, he goes over here, right? And what happens if he goes over here? It's game over for this guy. Why is it game over for this guy? Because if you have a piece of silicon, you usually have this band gap. You have this conduction and valence band, which are present because there's a uniform crystal lattice present. But whenever you go to the surface, you have these dangling states. So basically, the periodicity of the lattice breaks over here, and that results in formation of these surface states at the surface. And these surface states are excellent recombination centers. So whenever electrons reaches here, it can use one of these surface states. It can utilize this to recombine with these electrons present in the valence band. So as soon as a carrier reaches this unpassivated surface, it's game over for this guy. So all these carriers which were, we wanted to collect our carriers here, but in the process, some of these carriers end up going at the surface, and they are basically just recombined. So then the next evolution in this cell design was to passivate this emitter. And the way it was done was basically you take your cell and put a thin layer of silicon dioxide on top. And the silicon dioxide is essentially as you might know from semiconductor, that's the best passivation you can get for silicon. So since it's a native oxide, it passivates many of these dangling bonds which are present on the surface, and you get a large reduction in these number of surface states. The matrix that is used to measure this is called the surface recombination velocity. So you get a large decrease in your surface recombination velocity, signifying that these surface states have been passivated. And then when you put your silicon dioxide, you cut it across where you need to make these, where you need to put the metal, and this is what's called the passivated emitter solar cell, or since we all like abbreviation, this was abbreviated as PES. And most of the cells, in fact, that you buy, even today, most of the cells which are made by companies like Suntech, Yingli, Trina, they're still over here. They have not evolved much more from, and I'll explain why. But a lot of the cells that you buy in the market are still at this stage of evolution. Okay, so now we have evolved to this PESC cell. So it's this PESC cell, and I have this P plus diffusion from the back coming from this aluminum alloy. I have this N plus from the top, but I also have this thin oxide layer over here that I've introduced to passivate my front surface. Right now, what's the, I've passivated the front surface, but how about the back surface, right? That's still the problem with this design, is the rear surface is still allowing for recombination, because I've covered the whole rear surface with aluminum. That's my contact over there. So this back contact is where a lot of surface recombination can still happen. So this was the next evolution in the cell design. So instead of just passivating the front surface, people also, some people, not all of them, but some people started to passivate this back surface also. And then you open up parts of it where you want to contact it. And that's called the passivated emitter, plus now you have passivated the rear as well. So passivated emitter plus the rear, so it's called a PERC cell, right? And this basically achieves both passivation at the front and passivation at the back. And then the final evolution of that was, so now I've passivated my front and my back. The other thing I can further optimize is that, so I told you before that we don't want this, whatever is generated over here is essentially lost, right? Whatever is generated in this diffusion regions is not collected out from the device. So you want to minimize this diffusion region. So instead of having a uniform diffusion, for example, instead of having this uniform P plus layer over here, what I'll do is essentially I only will locally diffuse where I want to put my metal contact. Just below those metal contact, I'll just restrict my diffusion regions to just those localized areas. And this is called the passivated emitter rear localized diffuse cell. That's quite a mouthful. A good way to remember that is the PERC cell. So this is the best, this is the best design you can get in terms of you have passivated your surfaces, you have restricted your diffusion region, and so this was the record setting cell, which was demonstrated by this group, University of New South Wales. It's a very prominent group. Martin Green is the leader of that group, and this achieved a record efficiency of 95%. I think it still holds the record for this efficiency. And you can see all the nice features that we discussed over here. So you see these localized P plus contacts over here. Similarly, you see these localized N plus contacts over here. You see these inverted pyramid structures, which we'll talk about in the next class, which are there to optimize the light trapping. But this is the best, in terms of cell design, this is the best you could do, with just one thing remaining. And that one thing remaining was, can somebody point out what can I do further? Yeah, so the only thing, in terms of passivation, everything, this is a very good design, but people are still used to thinking of, the cell as being this N plus P and P plus cell. So they were used to thinking of this diffusion from the top. And the problem with that is these fingers that you have to put on the top, and they reflect some amount of light, plus plus you cannot, so there's this trade-off in terms of these finger placements. So you want them to be in terms of this resistive loss, you want them to be as close to each other. But if you make them as close to each other and make many of them, you'll essentially lose out a large, or you'll just reflect back a large amount of light. So there's this trade-off which is always happens when you place these emitter fingers on the top. And the cells that you'll get for your testing in for your project, they are essentially, they are these top contacted cells, and you'll see clearly that around 6 to 7% of the area on the top is essentially covered with these metal fingers. And the trade-off is clearly over here. So if you increase your finger spacing, if you place them farther apart, then you get a large amount of sheet resistance. You get a large amount of resistance between these fingers. Versus if you place them close to each other, then you get a lot of shading. So there's this trade-off between shading and the resistance, the sheet resistance. And the way it plays out in this IV characteristics is that I can write my IV relationship as basically this formula. Let's say e to power q. So I've basically, what I've done is I've taken my Shockley-Queisser formula and written it more in a form where I apply 0 voltage, I get the JSC, and when I apply, so basically I've rearranged it so that when I apply 0 voltage, I get this short circuit current. And people who are more used to semiconductors write this way anyway. So now what happens if I have a series resistance? So if I have a series resistance coming due to these fingers placed large apart, fingers placed farther apart from each other, then instead of this V, I'll get a voltage. When I actually apply a voltage, the voltage I'll get across the cell is essentially this. So my revised equation would become right. So instead of having a dependence on QV by KT, I'll have a dependence on V minus IRS by KT. And how the way it affects this IV relationship. So basically, if this was my original starting my diode characteristic, this is plotting it for dark when there's no light shining on the cell. When I essentially when I have the series resistance, now this curve becomes much less steeper. Or you see that there's a degradation in the slope of this curve, because for achieving the same amount of current, I need to apply a higher voltage, right? And this is how it shows up in when you apply the light, that you had this sharper rectangular looking region before, and now since you have this series resistance, now it becomes this red curve over here. Right, and this is another chart plotting the same. So this is plotting that same IV relationship, and as I am increasing my series resistance, you can see that it's becoming more and more, instead of being sharp, it's becoming more and more flatter. And that essentially my maximum power point, which occurs when I have the maximum product of my JSC and VOC, that's when I have the maximum product of my current and the voltage, that's also moving along this trajectory, and my efficiency is accordingly decreasing as well. So this is the problem with finger optimization. So you want a less series resistance, but at the same time, if you do that, then you will get a lot of shading. So this is where the SunPower cell came along in 1984. So they did two things. One was their design was essentially they took the cell and flipped it around. So instead of the light, I've just drawn it that way. Instead of the light coming from the top, now you think of it coming from the bottom. And both of your N plus and P plus contacts are located on the top. And they had this very intelligent design in terms of routing these contacts called interdigitated back contacts. It's more of a design which is borrowed from IC industry. So it was used in BJTs also a long time back. So you have this interdigited back contact. So you get a very less amount of resistive loss over here. And at the same time, since the light is all coming from, there's no restriction in the path of this light, there is no effect of shading. So they did not just this, but they were able to do this with a low processing cost, and that was another key feature over here, right? And if you think about this cell now, it looks very much like an integrated circuit. So the way integrated circuits are done is like you have these metal contacts coming on the top, and then you can mount them on a printed circuit board because all these contacts at the top, so you can very easily mount them on a printed circuit board. Similarly, if you have the SunPower cell, basically you can just take a piece of like a printed board or a piece which is already your placement for these cells are already printed over there, and you can just come there and just place your cells. And that makes your assembly also that makes the assembly of your module also much more easier, because now you can think of this like an IC, you take it and you plug it on your board, and that makes your module assembly much easier as well. So this is a slide I've stolen from Dick Swanson. So it shows basically all the losses which occur in the backside back surface field kind of design, which is the PESC kind of design. So you lose around 8% of your efficiency by not 8%, 1.8% of this efficiency points by just reflections. Then you get reflections from this metal finger. You get reflections from the surface. You get this I square R loss because again you have to optimize between the shading and the I square R loss or the resistive loss. And then you get a large amount of these things. Since there's no emitter passivation, they're recombining at the back as well. Similarly, since there's diffusion region present over here, so this is my diffusion region present over here, so some part of them will get absorbed over here, and that's also again all these things are adding up. And ideally, as I discussed, this is my TJ limit, the TJ Eli Yablonovich limit, and that is 29%. But if you combine all these losses, I'm losing around 14%. I'm losing around 14%, and what I get is around 15%. So those were where the efficiencies of these passivated emitter cells were. And then what SunPower did was they essentially flipped the design around. So instead of having these N plus diffusion on the top, you have these localized P plus and N plus diffusion. You have the passivated emitter. You also have a passivated back layer. So you're passivating both the front and the back using this silicon oxide. And they were able to generate around 25% efficiency using this. And the losses are also pretty minimal. So you see over here the loss which was due to that reflected light, that has reduced substantially. It has gone down from 1.8% to 0.5% efficiency point. Similarly, your loss due to that diffusion loss in the front surface, that has gone down. Your everything looks much better, and you only lose around 4.4% if you combine all this. Yes. So one is basically the silicon nitride plus SiO2, right? And the other is this localized P-type diffusion, which is done on the top. So there is over here. Right. So this is my silicon nitride, my passivating layer plus my silicon nitride. So my passivation layer is silicon oxide, and then I put an anti-reflective coating with the silicon nitride, which we'll cover in the next lecture. And then below that I have this diffusion. My if it's an N-type substrate, I have this P plus diffusion from the top. And if you're pointing that why is there this diffusion in the SunPower cell, is that the question you're referring to? Yeah. So they still don't they reduce this diffusion, but they don't completely get rid of this even in the SunPower design. And the reason is that you still need this field over here to push your carriers away from the surface, because your surface recombination velocity is decent, but it's not excellent. So you don't want your carriers to still go at the surface. So you need that field provided by this p-n junction to repel the carriers away from the surface. That's why it's still present. They don't completely get rid of it, and you lose some amount of efficiency over here. But if you didn't put it, you'll actually lose much more because of your carrier going right to the surface. It's a very good question. Thanks for asking.